Good morning. This week's lab, we are looking at atomic spectra. So what we're doing is, well, in class, we've been looking at atoms and molecules, and atoms mostly so far, and identifying where the different quantum states are in terms of energy. What are the different energies of all the possible quantum states, specifically for the electrons? So this has to do with how the electrons are interacting with the nucleus and how the electrons are interacting with other electrons. And that ends up defining a set of quantum states, different possible energies that the electrons could have. Now, when we're measuring atomic spectra, what that specifically refers to is, well, each different type of atom is going to have a distinct set of energy states, of energy quantum states for the electrons. So what could happen is, let's look at some, some simple examples. We're going to be looking at samples of hydrogen, helium, argon, and mercury. Now hydrogen, as you guys may or may not know, that hydrogen, that we work with is molecular. It's H2. So we've got to find some way to take the H2 molecules apart so that what we're identifying are just individual atoms of hydrogen. For helium and argon, that's already taken care of. These are inert gases, or what we now refer to, I guess, as noble gases. So in that case, the helium and argon atoms already stay individual from each other. And then we have sample of mercury. Now you think of mercury as it's going to be mercury vapor. So the mercury vapor also will consist of just individual atoms of mercury. Now for each of these different elements, there's going to be some number of different quantum states. What I've tried to draw here was the ionization level. I don't know how well I did that. I have something, let me remove this transition. What we're trying to say is that there's a set of different quantum states. Maybe this is 1s, and 2s, and 3s, and this is 2p, and this is 3p, and this is 3d, or whatever. And electrons, if it's hydrogen, for example, what we could do is we could excite the electrons into excited states, higher energy states, and then the electrons will drop back down into lower states, and when they do, they're going to emit photons of a particular energy. So whatever the energy separation is between those two quantum states, that's going to determine the energy of the photons that are being generated. So, what color should we use for photons? Let's say we're going from this quantum state to this quantum state. There's a definite difference in energy, and that energy will show up as a photon being created during that transition. So what we're going to be measuring are, well, the photons. Now, we're not going to be directly measuring their energy. Instead, we'll measure their wavelength. And the way we can measure the wavelength for these photons is, if you remember a few chapters back, when we were introducing interference effects with photons, we introduced these multi-source interference devices. We call them diffraction gratings. And if you remember, for a diffraction grating, we can have a beam of light coming in towards a diffraction grating. Here's the diffraction grating in our setup. And then depending on the wavelength of the light will end up with, they're going to be peaks that are generated in very specific directions. So there's going to be, let's take one of these examples here. Well, let's see what they look like, what some of the samples look like. Okay, here is my favorite sample, and that's helium. You guys can see that, right? Let me check and make sure here. So that's helium, and if you notice, the helium, oh my gosh, I'm out of view there. There's the helium. So let me get a little bit of a close-up on the helium. So what we have here are what we call gas discharge tubes. It sounds cool. It's a high voltage device. And what we're doing is we're taking a sample of these elemental vapors, and then we are running some high voltage electricity through them. So we're using a high voltage to drive current through these. And what that does is it generates a bunch of electrons. And we're going to come back to recenter this in a minute. And so what's happening is we're exciting the electrons into these higher energy quantum states, and then photons are being generated as we drop down. Now, just for a side-by-side comparison, this is a sample of hydrogen. And so you can see, first of all, the helium's just a lot brighter. I guess I could turn the lights down too if I can figure that out. So you can see that the helium is a lot brighter, and it's different color. So I always think of helium as being, it looks kind of white. It turns out that helium's spectrum looks something like this. So here's a chart of different elements, and it's showing what their atomic spectra look like. Here's mercury, that was on our list. Here's helium, hydrogen, who else was there? Argon, okay, which is not on this particular list. But looking at helium, I guess, there was a line that's generated kind of off in the violet, and then one in the blue, one in the green, yellow, orange, red. Now, of course, it's a whole spectrum of colors. So when you say violet or blue, there could be a range of possible wavelengths there. We're just using those colors as a way to identify the lines. Because what's going to happen here is this. What we can do is we can take one of these, maybe I'll take the helium example. So I'm going to take the helium example, I'm going to take it and set it up next to, well, I got these meter sticks set up. And what's happening with this is, let's do a top view. So this is as if we're up here looking down on our setup. And what's happening is I've got a meter stick set up kind of perpendicularly, and then here is the light being generated. What I'm going to be able to do is, I want to be able to take one of my diffraction gratings and set that at a certain location. Now we'll get a stand set up so that we can get more careful measurements made. But when I look through this, and to do this, I guess I better turn the lights down again. So when I look through this, it worked last time. There we go. When I look through this diffraction grating, what it looks like is there are lines of color hovering in space. Now, why is that happening? Well, here comes the light from the helium. Of course, it's heading in all directions. But the light that reaches the diffraction grating, let's see, it turns out that, yeah, helium has the, a blue line, a green line, a yellow line, a red line. They all end up being directed at different angles. Now, when I put my eye here and I take a look at the light being generated, it looks as if the light is coming from over here. So it's a pretty cool effect. What you can do is you can set these up and get out the diffraction grating, take a look at the light that's coming out, and I go, oh my gosh, look at that. There is the blue line, and there's a violet line, blue, green. The yellow is very prominent. The red I can see really well. So yeah, I can pretty much see all of the wavelengths, all of the different color spectral lines that are showing up on this reference spectrum analysis table. So that's the idea here, right? Is that we'll be able to hold up those diffraction gratings. We'll get them placed more securely. But the idea then would be to hold up those diffraction gratings. Ooh, I can see my shadow on the front door. So I'm going to go ahead and turn these off now. These were just some to look at, see what they look like. So the idea here then is I've got this meter stick set up here, which is 1 meter. I've got it set right at the 50 centimeter mark in the middle. And then I set up another meter stick. Now, what I'm going to do is this. It turns out it's easier to see the spectral lines. We turn the lights down. It's going to be easier to see the spectral lines when I get close. Now, once I've gotten an idea of what that pattern of spectral lines looks like, I can bring my diffraction grating back. Now, I could come all the way out to 1 meter and then look and see what lines I've got. Maybe that doesn't work. Maybe I want to go to 50 centimeters or 60 centimeters or 70 centimeters. We'll have to see where we're able to make those measurements from. Again, the plan right now would be to come all the way out to 1 meter, but there's a couple of difficulties that we might run into. Maybe they're too faint and the lines just aren't very visible anymore. So we'll try. We're fairly flexible right now with that. Now, I do have this meter stick set up, and I've got the diffraction grating set at 1 meter right now, but that can be brought in. That distance I'm going to call A. And then the distance from the center, from the 50 centimeter mark, out to where these different lines of color, these spectral lines, appear to be hovering in space, I'm going to call that B. So here's my data sample. Let's say that we're looking at the helium, and there's a blue line and a green line and a yellow and a red line that we want to go in and collect data for. Well, I'll write down what the A measurement is for that measurement. I'll write down what the B value is. Coming back to my diagram, I can see tan theta is equal to B over A. So once I've once I've done the measurements of B and A, I can use this formula here to determine what angle I'm looking at. So that's going to give me a theta. Now, one warning here is, I know the textbook likes to, whenever possible, use these small angle approximations, but these are not going to be small angles, so I can't use the small angle approximations for this. In any case, there is the theta that we're going to measure. So keep these as 2 distinct measurements, or 2 distinct calculations. And then once I got the theta figured out, I can get the wavelength. I'm going to need to have a value of D. So let me get that written in also. Now, it turns out we have 2 different types of diffraction gratings. They have different values of D. One of them, the D value is a little longer. It's around 1900 nanometers. I think on the others, let me check. I think these are closer to 1100 versus, anyway, those numbers will get written down. We'll write those down in the, all this information will either be in the data sheet or it will be in the slides. One or the other should be in the data sheet for this. So I do need to know the D value for my diffraction gratings. And then I can come up with wavelengths. So that's how we're going to go in and be able to calculate a wavelength based on these measurements of A and D. Okay, so it should be pretty cool. And then once we've got that, we can come back and compare with accepted values. Now, I kind of like just working from the chart here. I can kind of estimate from this chart what the accepted values would be. Now, what I also did, and I think this is just going to show up as part of our slides, or part of the data, it'll show up in one of those. Here's a set of accepted values that I found online, where the wavelengths are measured down to tenths of nanometers. So that's maybe more reliable from just estimating from the chart. In any case, that's kind of the story here, is that think about what we're actually measuring here. We're looking at differences of energy between the quantum states. Now, again, referring back to what we've been talking about in class, for hydrogen is simple enough. Hydrogen just has 1 electron. Hydrogen is simple enough that we have formulas from from solving the Schrodinger equation, or even from the Bohr model. We have formulas for the energies of the different levels, the quantum levels of the electron energies in hydrogen. So there we can actually do a comparison with the theoretical values we have from the Schrodinger equation. Now for the others, when you start adding more electrons in, things get complicated. So, and this is what we've been talking about in chapter 39, I guess is where we are, with atomic the quantum mechanics of atoms. And so there, we're mapping out these energies, but the theoretical predictions are pretty difficult to carry out. So instead, we're just using accepted values that other people have measured. So I think that takes us through everything. I don't know if we've left anything out. So let me stop there, and then I'll get one of these set up on some of the tables here, and we'll take a look at what taking the measurements looks like. So here's what the setup looks like on one of the tables. So I have taken the helium sample. I've got the helium sample in the high voltage mount. Be careful with this. Make sure that it's unplugged before inserting the tubes or removing the tubes. This is what the tubes look like. So we've got a series of these, and as we stated, we're going to be looking at hydrogen, helium, argon, and mercury. That's what the individual tubes look like, and then we can place them inside the high voltage device. And then I just got a couple of bricks here. I have been careful to set up the meter stick, so the 50 centimeters is right in the middle, and then you can see that I've got a meter stick set up so we can measure the distance from the measuring meter stick out to where the diffraction grating is going to be placed. Now, I'm using a diffraction grating right now. I'm using the one with the shorter D value, and what that's doing is it's creating larger angles. So in order to get all of the lines to show up on my meter stick, I've brought that in. So I've brought that into like the 50 centimeter mark right there. And I'll turn the lights out and we'll take a look and see what it looks like with the lights out. All right, I've turned the lights out. The camera, I hope, is working pretty well in this low light. There is the sample, nice and bright. The helium atoms are emitting all those photons. Now, when I look at that, it looks to me kind of like white light, but as we've talked about, it's really a combination of very distinct lines in different parts of the spectrum. I'm going to take the camera here and just to see if we can get actually an image of what you would see. So I'm going to bring the camera up to the diffraction grating. The diffraction grating is right there. And look inside, and when I turn to the side, there they are. Look at that. Red, yellow, green, blue, those four really prominent lines of helium. And it's kind of interesting, right, that as long as there are lines from each part of the spectrum showing up, we interpret that as white light. We can't tell the difference between just a few distinct lines showing up in the spectrum versus, having the entire spectrum filled in. So, yeah, I didn't realize it was going to be that manageable, but there they are. Okay, so I don't know if you guys can see this from the camera, but here in the room, you can take a look at those lines and you can see what location on the meter stick those are hovering over, and we can get the measurements that we need, right? So we're set up here with what? A is equal to 50 centimeters on this particular measurement. I'll have to go in and see which values of A I want to work with, or if I want to switch diffraction gratings. And then once we look through the diffraction grating, we can look and write down what locations on the meter stick those lines appear to be hovering over. Those lines align with particular locations on the meter stick. All right, so that's the setup. That's what things look like. If you guys have any questions, stop by office hours. We can certainly discuss any of the setup, any of the setup or any of the theory behind what measurements we're taking in lab today.